Hi, I'm Ethan Fish, and this is my challenge assessment 2, the wall insulation. Okay, so here we have our problem statement and our goals. So we'll start with the problem statement. 4-meter high and 6-meter long walls constructed of two large 2-centimeter thick steel plates, which you can see right here. They're given K value, separated by 1 centimeter thick, 20 centimeter wide steel bars placed 99 meters apart. Remaining space between the steel plates is filled with fiberglass insulation, which you can see here, 20 centimeters apart. There, and fiberglass is given K value there. The temperature difference between the inner and outer surfaces of the wall is 22 degrees Celsius. Determine the rate of heat transfer through the wall. Can we ignore the steel bars between the plates in heat transfer analysis since they occupy only 1% of the heat transfer surface area? So then we get into our goals and kind of what we're trying to look for. We want to determine the rate of heat transfer through the wall. And then is it possible to ignore the steel plates between the plates? The steel bars between the plates? And we want to model this wall as a thermal resistance network. We want to find the temperatures at the edges of different materials. We want to adjust 3 parameters to analyze their effects and kind of optimize this wall and see what happens. We want to analyze a different insulation material instead of fiberglass to see if it'd be more beneficial or if fiberglass would be the best option for us right now. And then my goal that I made for this wall is I want to have the inside of the wall cooler than the outside of the wall. And then for our final goal, we'll have a redesigning of this wall and kind of optimize what we have. Okay, so here we have a modeled thermal resistance network for that wall that you just saw. So going from left to right here, we have T1, which would be on the left-hand side of the wall, and then we have the resistance of that plate. And then in the middle here, we have resistance in parallel, which would be the steel bars and the insulation. And then you jump past that into the other plate on the right-hand side. And then you have T2 on the outside. When you look at that, you think this is kind of messy, it'd be kind of hard to calculate. Well, with resistors in parallel, there's an equation you can use to make this R equivalent, so make that equal 1 number, which would then end up looking like this on the right-hand side here. And it's nice resistors in series, so you just add them up to get your R total. Okay. For our calculations, they were done in MATLAB, and that's where we got all of our numbers, and that's where all our calculations were done. Calculated the heat transfer across the wall, temperatures at the edges, and then we did a calculation to prove that you could not neglect the steel bars when calculating heat transfer across the wall. Okay, here we are. This is the analysis of the wall. The graph here displays temperatures points across the wall. So 1, 2, 3, and 4. And as you can see here, there's a big downward trend, which is good because when I originally talked about the goals here, we wanted the inside of the wall to be cooler. So you say this is the outside world, it's 22 degrees Celsius, and we want to maintain that 0 degrees Celsius inside the room. So we have that heat transfer rate of 486.27 that is going through this wall to allow this room to stay at 0 degrees. Okay, and then I did some parameter modifications here to kind of see how would you optimize a wall here and what's really going on. So the graph here shows what happens when the thickness of the walls, bars, and insulation are changed. So the temperature difference across the wall. When the bars increase, the insulation will also be increased. That's kind of a side note because the 20 centimeters in the middle that you saw in the first slide, that's the bars and the insulation thickness. So that's just kind of a inside checkpoint. And then due to the objective of trying to have the inside of the wall be a constant 0 degrees Celsius while changing temperature is changing, Okay, so getting to kind of the modifications that were made. They were all modifications were the same, like what was changing for each test, but we just changed the numbers. The first two here, we increased the thicknesses and the temperature difference. This was also increased, and then the bottom two, we had a decrease to kind of see like what would happen that way to kind of fully understand this problem. Okay, so modification 1, which is that red one right here, we increased the wall thickness from 2 centimeters to 5 centimeters. We increased the bars and insulation thickness from 20 centimeters to 50 centimeters, and temperature difference from 22 degrees to 33 degrees. As you can see here, that temperature jumped up to that 33, and there's a small drop from temperature 1 to temperature 2, which is kind of hard to see from this set of numbers, but there is a small drop, along with 3 to 4, which is obviously hard to see here because they all kind of merge into the same location, but there's a small, very small drop. Okay, and then you can see here I also included the heat transfer rates for when the wall was getting thicker and thicker. So as you can see, it's getting smaller and smaller when the wall is thicker, because that heat has more area to travel through, which is lowering that heat transfer rate, because that area is much larger. And obviously the resistance is a result of that too. You calculate for the area, that makes the resistance larger. Okay, and then as you can see here, modification 2, heat transfer temperature difference was substantially higher, so that heat transfer rate was 259. And you can see here that we changed the thickness pretty high too as well. So then we'll go down here to modification 3 with the thinner wall. We went from a 2 centimeter wide or thick wall to a 1 centimeter wide thick wall. And then we went from the bars insulation, we went from 20 centimeters to 15 centimeters, and temperature difference from 22 to 15. Okay, modification 3 is this one right here. And this one right here is original. I should have put that out earlier. So this is the original one with fiberglass right here. So modification 3, which with the thickness changes I just told you and temperature difference I told you, that Q dot went up substantially when we shrunk that wall, because the area is much smaller. You kind of see that transitioning from here, and as you can see here, this is kind of off topic, but the slopes for each one of these has changed as you went from modification to modification, which is a resultant of that heat transfer rate. The smaller the heat transfer rate, the steeper that slope. Okay, so now, can we really ignore the steel bars? Well, although they only take up 1% of the area, the heat transfer rate without the bars is substantially smaller than with the bars. So pretty much they're acting as a thermal bridge. So Q dot with the bars was 486.24, and then you calculate it without the bars, that's 91.416. So that's a huge change. And I mean, that's obviously, if you need to calculate it with that and you forget it, that's your number's gonna be way off. So you cannot ignore the steel bars. Okay. They also tested a different insulation material besides the fiberglass. We went with, I researched and found hempcrete, which is a mixture of hemp herds or shives and some lime. It's an insulator, and a moisture regulator. But a couple of cons is it lacks brittleness and has a very high density. As you can see a picture of it right here. Along with the fiberglass, we also ran some analysis on this just to kind of see how it looked. So I have some reference data in here to kind of see the differences from down here. K value is obviously larger than the fiberglass, which would make this not as resistant, and overall, I mean, think as well a worse insulator. Depending on the application, it might be suitable, but for this application itself, it wouldn't be quite suitable. So fiberglass would be better, but the overall data, I mean, it looks very well similar. Just looking at this graph, you can take a look at the heat transfer rates, the thermal resistance. I mean, it's much different. So something to kind of consider when you're doing these studies. All right, and then we have wall redesign. Looking at a complete wall redesign, there are multiple things that can be considered, obviously, which would be the material and the thickness and much more. So as a goal to maintain a constant temperature inside the wall, studies must be conducted, obviously, on like kind of what the wall needs to be done or the properties of this wall. So I determined that thicker walls would be better to achieve my goal of keeping that inside colder. We'll have a lower heat transfer rate, which will prove to have more insulation. Um, Insulation meaning it'll keep it temperature difference from the outside to the inside larger. Um, we'll find the optimal insulation based on K and R values. The smaller the K value and the larger the R value. That's what our goal would be for this the insulation that we put into our wall here. So fiberglass has proved to be a good one, so we would stay with the fiberglass. I would imagine. There may be something I've never even heard of that would be better, but that's how I would redesign my wall. Thank you.